Thank you very much, sir.
Yeah, good evening.
Good evening, sir.
Good evening, Tarun ji.
Sir,
I congratulate on behalf of our Maharishi Markandeya Deemed University management and on behalf of our Vice Chancellor for the Department of Electronics and Communication for organizing a faculty development program on fundamentals of digital VLSI design. This is one of the prime area for any electronics engineer or teacher has to update the knowledge in the digital VLSI. And I take this opportunity to convey my best wishes to EC department and HOD Dr. Tarunji, who is also Director IQAC, and also the resource person is also from our EC department, and all the participants from the different walks of the different institutes across the pan-India. So we believe in the quality, the Maharishi Markandeya University always. And also I believe in personally, teachers should learn something continuously. When we are not learning any one day, it means we are dead like that. So I request all the faculty who are participating, all the participants in this workshop to take the advantage of this online workshop on hands-on also in the physical for the practical sessions. Just now Tarunji told to learn something more on the not only analog. Now this is a digital VLSI design where it is very important for upcoming days. Once again, I congratulate and I request all the participants make use of this workshop organized by the Department of Electronics Communication of the Maharishi Markandeya Deemed University. Thank you for giving me an opportunity, Tarunji and the resource person. Thank you so much.
thank you very much, sir. Thank you for sparing your valuable time, sir.
Thank you.
We are extremely pleased to see such enthusiastic participation from students, researchers, and also professionals who wish to strengthen their understanding of VLSI principle, a domain that continues to shape the future of semiconductor technology. Over the next 2 weeks, this workshop will provide a comprehensive foundation in digital VLSI concepts, hands-on exposure to design and methodologies, and valuable insights. We hope this learning experience will not only enrich your technical knowledge, but also inspire you to explore new possibilities in the realm of digital design. Once again, a warm welcome to all. We look forward to your active participation and engaging and productive workshop ahead. Thank you.
Thank you very much, Honorable Pro Vice Chancellor Sir, for your encouraging words and for always supporting the electronics department and every department within the MMDU. And thank you so much, Sarun Gulati Sir, for your insightful message and for your constant guidance in the department for all our initiatives. Your words truly motivate us. Thank you so much.
Thank you, sir. Sir, how many participants have joined in this workshop?
Sir, as of now, what I can see is 35 participants have joined already, and we are expecting 45 here. Probably 5 to 10 participants would be joining within the few minutes.
And from where these participants are belongs?
These participants are actually from the various parts of India, from southern part of universities, from a few are from the NITs, a few are from IITs, one is from Germany, and from MMU and the other northern universities also.
Thank you, sir.
Thank you. So participants, I welcome you here to this workshop, and please let me know if the screen is visible and am I audible to you all, so that we can start immediately. If someone of you can take the initiative and can write in the chat box.
Yes, sir.
Perfect. So if I'm audible, I'll be starting from here. Listen, a few things before starting to this workshop. The first thing is that you can ask your question anytime, and it would be better if you do not interrupt when the topic is going, and you can write your query in chat box. If after every topic, I'll come to the chat box and we'll try to revert your query, so that you do not miss that particular topic for in the continuation for the next. You please keep writing your doubts, and if you're not satisfied with the answer that you get, I welcome you to turn on your mic and ask your query in any language. You can go in Hindi, English, Punjabi, whatever language you're comfortable with. I would try to explain the topic, and I'll try to take on your problem and try to answer it as best as I can. Right? I would expect that everyone would take part in this very in a very uh, encouraging manner. And please, because I decided to have this workshop in Hindi plus English, but when I see that there are a few participants from the southern part of India and they may not be well conversant with English, so well conversant with Hindi. So I had decided that I will speak on this workshop completely in English. And if you are looking forward for any query that you do not understand or any topic you do not understand, you can request. I can explain it in your mother tongue, right? So let us start with the first topic first in this. That why we are studying this course, basically studying this understanding. What we are going to do is we are going to work on the physical design. And please believe me that understanding that transistor that powers the modern electronics is not optional. There was a time when we were taking it as an optional subject, that one can study, you say, communication, one can study some other topic and can get away with the MOSFETs. But the time has come that India is consistently working on the ICs and the semiconductor design. So learning the transistor is no longer optional. See, it is essential for everyone who is serious about the semiconductors. India is not going to enter. India has already entered into the era of semiconductor. So it is very essential for every engineering student, maybe from first year or it's from final year, that it is very important that you should learn about this semiconductor design. And we will try that this course will bridge the critical gap between abstract theory and the practical device operation. See, whatever we'll do in our practical sessions, we'll try to explain everything in the theory so that there is no gap between theory and what we do. In semiconductor studies, what actually is missing is that whenever you do any practical or whenever you do anything, whenever you study anything theory, there is always a gap between what you study and what you do in practicals. In this particular workshop, we'll try to connect both. We have kept 7 or 8 practicals in this workshop, and we'll try to decode every output that we are getting in the laboratory. And we'll try to design a circuit, we'll try to analyze it, and we'll try to optimize it. See, these are all different terms that one need to understand. Designing is something that you need to conceive the design, and analyzing something that when you have a particular design and you are getting the outputs and you are trying to connect it with theory. So that is the analyzing. And optimizing it, that now you know how to design, now you know what is the analysis. Now you can optimize it for power, you can optimize it for performance, for the any real world circuit. We'll do some real world circuits with you, and I promise you that each one of you will learn how to create a new circuit from this workshop. And your journey from nanoscale MOSFET physics all the way to the memory design applications will prepare you for the advanced tools. How? We'll be studying from the long channel, that is the 180 nanometer, and we'll go up to 18 nanometer, that is called the short channel. See, when there was a time of 180 nanometer, people used to call 65 nanometer is a short channel device. Now, see, 65 nanometer was a short channel device. What about today's Intel 2.5 nanometer transistor? Is it the shorter device? The simple answer is no, it is the actual short channel device where your channel length reduces to 2.5 nanometer. Now, what is the meaning of 2.5 nanometer channel length? We'll see. See, the point is before talking about the 2.5 nanometer channel length, we need to understand that why we are focusing on MOSFET, why not on BJT, why not on GFET, why I am not focusing on FinFET, why I am not focusing on the current device, which is CNT FET, why I am not focusing on GNR FET. There are Ferris FE FET. See, there are hundreds of MOSFET types are available, but we are going to focus on this CMOS MOSFET only. The only reason is that this is the base device that will give you the understanding of each and every device. How we do that? Why we are because industry dominance in current scenario, even today, when we are talking about the FinFET, CNT-FETs and GNR-FETs, industry is still producing the CMOS devices. This MOSFET is the backbone of our semiconductor technology today. And this CMOS technology, you should remember the people who have already studied the digital electronics, they might have studied a topic which is called the logic family. In this logic family, you have studied about various families that is called TTL, ECL, and the other families. And there you might have studied about CMOS family. Why the CMOS family was important? Because CMOS family used to give you the low power devices. And low power devices plus they have the superior performance. Now, what I mean performance in a processor, in processor performance means speed. There are three things in a device. One is speed, one is power, and one is area. Every semiconductor engineer looks to have a trade-off between the three. If you try to minimize the power, the speed increases. If you try to optimize the speed, the power start getting increased. I'll tell you how this happens. Don't worry. I'll give you every bit of it that if I increase the power, why speed decreases? Why the speed increases? If I decrease the power, why speed will decrease? And if you try to optimize both, you will see that you have to work with the area of the device. Your device get way broad. So every engineer has to make the balance between power, speed, and area. The other thing is that MOSFET is a voltage control device, and voltage control operation actually gives you the superior control over the devices. You get a lot of control. The BJTs were the current control devices, and these are the voltage control devices. And then the transistors has a quality that they can be copied very easily onto the layout. That is why there is a massive integration of transistors is possible within the memory chips, and this drives a Moore's law forward. Now we have seen two things. That one, that why we are studying the fundamentals of digital VLSI design course. I'll come back to that. That because this is no longer optional, and this will give you the option to design, analyze, and then to optimize. That you will do. Remember, this is our objective of this workshop. That we have to learn how to design a digital circuit and how to analyze it, then how to optimize it. Then our journey from nanoscale to the deep submicron devices. And then we have studied that why we are focusing on MOSFET. Everyone who is listening to this lecture, please understand that there can be a time in between these classes. In first 3-4 days, you might feel like bored of the physics of semiconductors. But this is something that is very important for a semiconductor engineer. Whenever you will sit in any viva of any interview of any company, any good company, be it a Micron, be it NXT, they will expect you to have a huge focus on the physics of MOSFET, which is very important. I'll try to make it as simple as possible. I'll not give you the dose of more than 40 minutes a day, but I'll give you the notes also. I'll give you the recording also. But please revise it. Please study it. What we have done today before coming tomorrow, so that you can connect both the things. Now let us come to the point. What is a MOSFET? Now in this particular slide, I am going to tell you that what you know about the MOSFET. Then I'll tell you what I wish to tell you about the MOSFET. Right? Now, in our earlier classes, what we have learned about the MOSFET is that it's a 4 terminal device. See, it is written that MOSFET is a 3 terminal, but MOSFET is a 4 terminal device, in which we have one terminal as source, one terminal as gate, one terminal as drain, then one terminal comes over here, which is called the body. There's a body of semiconductor. So there are 4 terminals in MOSFET. Why MOSFET is called MOSFET? Because there is a metal, there is oxide, there is semiconductor. And field effect transistor means it is driven by the voltage. Where is the metal? This you see these connections, this source, drain, and this gate. These all have the metal connections. These are the metal. And now you see this layer of oxide. This is SiO2. This brown color text is this. This is silicon dioxide. This wire is of metal. This is oxide. And there you see P-type semiconductor. So this becomes metal oxide semiconductor. And because this is driven by the voltage, we'll see, I'll show you in your practical this practical laboratory that this whole process is driven by this particular voltage only. That is why this is called voltage control device. Now, MOSFET, what is MOSFET in general? It is a metal oxide semiconductor and field effect transistor. Field effect transistor means it is a voltage control device. When you use it as a resistor, means you are talking about analog designs. And when you are talking about as a switch, it means you are going to work on a digital design. Everyone, please listen to this very patiently. Either you become an analog designer or you study about the fundamentals of digital VLSI. The MOSFET concepts are very important. Without MOSFET concepts, neither you can study about the digital VLSI nor analog VLSI. So mixed signal processing is obviously it becomes impossible without these. Now please understand that in this particular classes for first 3-4 days, we will be studying in deep about the MOSFET only, and then we'll build our concepts, that how to use these concepts and how to use these laboratories to create the digital circuits. And once you are able to create the digital circuits, you will be able to create the analog circuits yourself. Now, let us come to those components which we have studied the MOSFET. One is the gate terminal, one is source and drain, then there is channel region, then there is oxide layer. Now, please read these lines. I have written them for your reference, that the gate terminal is very important. I'll show you where the gate terminal is. This terminal in particular, this terminal, this is called the gate terminal. This terminal, the gate terminal, operates whole MOSFET. If there is not enough voltage on gate, then you cannot expect any MOSFET to work. So gate terminal is very important. That is why I have written gate terminal separately and source and drain together. Why source and drain together? You please see here. This is source and this is drain. In this MOSFET, source and drain actually look alike. एक जैसे दिखते हैं दोनों. That is why we have kept source and drain together. And believe me, very few people tell you this thing, that in this MOSFET, uh, if you connect this, if you connect this point on the voltage, this becomes drain. If you connect the voltage over here, this will become drain. If you ground this, this will become source. We'll see this in laboratory. And then there is a channel region which is found by the gate control voltage. And then there is the oxide layer. Oxide layer is very important because oxide layer is the one which creates the O of MOSFET. This. So this is the oxide layer, which here you will give voltage. This oxide layer will create the electric field, like capacitor sort of a thing. And then your MOSFET will start working. There are two types of MOSFET. One is enhancement MOSFET, one is depletion MOSFET. In majority devices, what we are going to study is enhancement MOSFET only. What is the difference between the two? That enhancement MOSFET requires some voltage to start working. But this depletion MOSFETs do not require any voltage. It keeps on working even on 0 volts. If this is the case, then why we are using this depletion MOSFET? See, in some cases, we want our MOSFET to work every time without giving any potential. Then we use depletion MOSFET. But in 99% cases in VLSI, we work with the enhancement MOSFET only. This is a N-type substrate, so this becomes P channel. If this is a P-type substrate, this becomes N channel. So what is the difference? In enhancement type MOSFET, you have to give some voltage, then you get the current. And in depletion type MOSFET, you do not give any voltage, still you get the current. So if you have to stop this current, you need to give the negative voltage. Right? Negative voltage means there is no negative voltage actually. You have to give the voltage with the reverse polarity. And I'll show you how this voltage polarity works. This is a MOS structure that we have seen a moment before. There you have P. See, if this is P type, it means it is a NMOS. If it is a N type, it means it's a PMOS. I'll come to this energy band diagram. This is very important part. Before that, I wish to show you that how this MOSFET works. See, this MOSFET is actually this device. You please consider this device. It is a 2D view of this device. There you have P-type substrate, means there are holes as majority carriers. Then this is oxide, and from here you give the voltage. Now, if you give less than 0 volts, less than 0 volts means that below 0 volt, there will be a negative voltage. And this negative voltage will attract the holes. And you have the holes at the majority carrier in P-type substrate, then it means your holes get accumulated over here. This is called accumulation. Now, what I do is, remember that I have given the negative voltage over here. Because of this negative voltage, the holes get attracted. Negative voltage will attract the positive holes. Opposite charges attract. Then you see, this is a depletion region. Now, what I have done is, I have given gate voltage, which is now greater than 0, means it is positive, but it is very small. Now, this positive voltage, what this positive voltage will do? This positive voltage will make the holes to repel, because same charges will repel each other. This gate voltage is positive and the holes are also positive. So these holes which were over here, they were here because of negative voltage. Now the voltage is positive. This positive charge has started repelling these holes, and there you see nothing. Initially there were holes, but now there is nothing. So since there is nothing here, So because there is nothing over here, that is why this region is called depletion. Depletion means there is nothing in this region. There were only the holes, and those holes are also repelled by the voltage. Now what I have done in this case, that I have now increased this positive voltage. I have made it very large. This large positive voltage has now attracted the minority electrons. This p-type silicon substrate has majority holes and minority electrons. So these minority electrons are accumulated over here, and because of this accumulation, this you have the electron layer over here, and wherever you get electrons flowing anywhere, that you see in the form of current. See, what is a current? Current is a flow of charge, and when you have the negative charge over here, you will see the flow of current. So from where we started that initially we had the negative voltage. This negative voltage has accumulated the holes over here. Holes do not contribute to the current. And then you have applied some small voltage. This small voltage, what it has done, it has started repelling the holes. It is not attracting the electrons. It is repelling the holes. Why? What is the meaning of repelling the holes? That the holes are of the positive charge. These are get repelled. Now there are no electrons here, no holes over here, means the region has got depleted. Now after the depletion, when you increase the voltage, it is large enough to attract the electrons from which are the minority in this p-type, and these electrons actually contribute to the current. That is how the current flows in the MOSFET. I hope you all have got the point. If you have any doubts still here, if you have anything you want to ask here, you please put your queries in the chat box. I'll try to revert. Then I'll come to these calculations and how these energy band diagrams work. Right? What we are trying to understand over here is that these energy band diagrams are very important. See, my timer is saying that after 2 minutes, probably this meeting will get over because of having the limit of 40 minutes. If this gets over, I would request everyone to please rejoin, because for 10 minutes, I want to make you understand the energy band diagram of MOSFET. Right? This is very important. We have studied only one thing today, that how the accumulation, depletion and inversion process works. And this is associated with the energy diagram of MOSFET. Okay, we'll study this energy band diagram of MOSFET tomorrow, right? After next 2-3 minutes, everyone please come over to the laboratory part and the link for the laboratory. We'll study the laboratory part today, and I'll explain you that how PMOS and NMOS work in the cadence, right? For today, that's all for the day. Tomorrow, I'll start with the energy band diagram for the MOS again, right? And I'll share all the PPTs, whatever I have taught you, and all the notes that I have, and this recording also. If you have any queries, do not post over here. Please post it in the chat box of laboratory. I'll start with your queries, and then I'll move towards the lab part, how this MOSFET works. Right? Thank you so much for this theory class. I'm going to turn it off, and I'm going to start the that laboratory Zoom link. Please come to that. Thank you so much.